Hello, my name's Arron, and today I'm going to talk about the STIG, or Steam Injection Gas Turbine Cycle. So just a quick overview on the history of steam injection and water injection into a gas turbine. In the early 20th century, they used to inject a water vapour into the compressor. This was to increase the mass flow rate and improve efficiency. And the STIG cycle we now use, where steam is injected into the combustion chamber instead of water into the compressor, came to be after a huge focus on research and development into improving fuel efficiency in the 1970s. So the oil crisis, or energy crisis, in 1973 meant that New Zealand, Australia, Japan, Europe and the United States faced a substantial oil shortage and inflated prices caused by interruptions in supply from the Middle East because of the war in Israel at the time. The results of the research and development efforts were the various methods of steam injection that is now commonly used in power plants, the most common being steam injection into the combustion chamber of the gas turbine. So we can see the massive increase in price of oil right around the beginning of the 70s. Continued that way into the 80s, where it started to decline, and we can see right around 2001 where it's ballooned again and is still not really recovered. So how does the STIG cycle work? Well, it's still the Brayton combustion cycle, like a typical gas turbine. We can see the PV diagram and TS diagram are still the same. So steam is injected into the combustion chamber, and that steam is typically produced by a heat recovery steam generator, and the steam increases the mass flow rate through the turbine to provide more power output. So it does this by increasing the rotational torque and increasing the mass flow through the turbine without needing an increased mass flow through the compressor, which would cost additional energy. The steam injection improves overall efficiency, anywhere from 15 to 30% compared to a simple gas cycle, and those efficiencies depend on the steam to air and steam to fuel ratio, but they typically run at 0.4 to 1 for a steam to air ratio, or 6 to 1 for the steam to fuel ratio. With the increased efficiency, you also get a improvement in the specific fuel consumption by normally up to 10%. So the steam injection also reduces nitrogen oxide emissions by reducing the combustion flame temperature. So not only are we getting an improved overall efficiency, a reduced fuel consumption, we're also getting a reduction in emissions. So current and potential use of the STIG cycle. So current use is often in a gas turbine power plant, where that waste heat from the exhaust would literally just be waste. So they utilize that in a HRSG to produce superheated steam and improve their efficiency. But they're also used in plants that generate their own power, whether that be because of reliability, backup power, or they have a huge power requirement, so they can make use of the steam injection to improve their efficiency and reduce costs as well. So a potential use of the STIG cycle is with a solar hybrid STIG cycle, where a HRSG is still used to generate the steam, but additional heat is captured through solar collectors to aid in that steam generation and improve efficiency even further. So what you can do there is you're not as limited by the exhaust temperature, so you can generate hotter and drier steam. There's a few articles I found online, fairly recent articles, so there's ongoing study on incorporating this sort of technology, but they're all behind paywalls, so I couldn't share any any detailed info on that. So despite the obvious benefits to using steam injection, there are some problems that need to be considered, which may not be a major issue in some situations, but in others could be a substantial factor, and that's water supply. For the steam injection to work properly without damage to the turbine, the water needs to be purified and filtered to stop any particles or impurities passing through to the turbine. So in places where water is in short supply or requires substantial processing before use, this can become a major hurdle in setting up a reliable STIG cycle power plant. It is normally required that a supply of purified water is produced on site to ensure supply is reliable and controlled. So provided that can be done, the STIG power cycle is an excellent choice. Okay, thank you very much for listening. If you have any questions, please feel free to ask.